As the last video for this lecture, let me now show you a code example implementing the softmax regression model from scratch using this vectorized form that I showed you to show you that it indeed works. Actually, I have two code notebooks here. One is a from scratch implementation using a simpler iris dataset. And then I will also, because I mentioned that before in the lecture, I will also show you the MNIST example because I'm sure you were all waiting for it. All right, so let's execute the boilerplate here first. Just getting it out of the way. And here, so the data loading, there's nothing really new going on. It's the same code I used for these toy datasets and the simpler iris dataset I used before, so I don't want to really spend too much time on discussing this again. It's essentially the same, only that this time we are using 3 classes instead of 2. So we have now these circles, upside down triangles and the squares. So left hand side is the training set, and the right hand side is the test set. In the other notebook I will show you also the PyTorch data loader. So that is then usually how we load data, because in deep learning we usually don't use CSV data sets, so we usually don't do this procedure. We usually use a data loader. I will show you in the next code notebook how that looks like. So starting with our low level from scratch implementation, computing the gradients manually. So here I just defined some helper functions, one that converts the class labels to a one-hot format, a softmax function, and the cross entropy as the loss function. Note that you don't have to implement any of that when you use PyTorch regularly. I mean the regular version of how people implement code in PyTorch, because PyTorch will do the one-hot encoding internally, kind of implicitly when we compute the loss. I will show you how that would look like later. And also it has the softmax and cross entropy function already implemented, so you don't have to worry about this yourself. I'm just doing it here to really show you that the mathematical concepts from this lecture really translate one-to-one into code, and it actually all works. So similar to logistic regression, we start with defining a class. So in the init constructor method, we construct the weights and the bias. So we initialize them here to all zeros. And notice that weights, in contrast to logistic regression, in this softmax regression context, it's now a matrix, right? So we have the matrix num classes, num features. So this is we used h, I think, for the number of classes, h times M matrix. And because we have also 2 net inputs for the 2 outputs, we also have now the bias as a vector, right? So this is a h-dimensional vector now. So h is the number of classes. And here's the forward method. So the forward method is computing the net inputs. So I call them logits, but these are, you can think of them as the net inputs. It's just the multiplication between the inputs and the weights plus the bias vector. So this would be an h-dimensional net inputs. So these are our z values here. Then I'm applying the softmax to get the probabilities. So the probabilities here, with that I mean these units A1 and A2, our activations. So we can also call them the activations, and these are our net inputs. And I'm returning both here. And here this is the interesting part, the backward method. That is where we compute our gradients. And instead of doing everything with a for loop for each weight individually, we can actually use the vectorized implementation I showed you. And let me move this over. I'm implementing it really one by one here, or I mean like literally. It's not making any change. We use our X transpose times, so with a matrix multiplication, times y minus probability. So probas is really the activations here. So this part is essentially this part here in the parentheses, and then also the transpose again. And this is exactly the same as I'm showing you on the slide. For the bias unit, it's a little bit simpler because the derivative doesn't include the x term, so we can just, so this is a vector, right? So we can just compute the sum. All right. This is it. So here in the predict labels thing. I'm just applying the argmax to get the index of the highest probability in the activations. So that's also what I explained to you earlier. I can actually move that back here. All right, so this is all that's new here really. The rest here is the same. So the evaluate function, that's the same as the one for logistic regression, and the training is also the same. Notice the only difference here for the train function, or train method, what I did is I added this one hot encoding here to get the one hot encoded class labels. But again, we call forward, then we call backward to get the gradients, and then we update the weights by applying the negative gradients, so minus the gradients times the learning rate. I'm also normalizing by the size of the mini batches, because I told you that is easier to find a good learning rate this way. And here this is just for logging, again to show our accuracy and loss during training. But again, this is actually not too complicated, right? I mean, if we look at the backward method, it's really just 2 lines of code here if we use the linear algebra compact vectorized form. I should actually mention this is not so trivial, of course, to think about what should go in here. It looks very simple, but it might take you hours and hours to think about it. So personally, in the first pass, if I would ever implement something from scratch, I would implement it in Python for loops and then go to the linear algebra implementation. I think that's maybe easier for me. Other people may find it easier to think about in these matrix and matrix multiplication terms. I personally, it's not my thing. I like things simpler, even they can be more verbose. But I'm using this, of course, because it's more compact. It's very information dense, lots of things going on here. It's more compact though and computationally more efficient. But again, also I should say in practice, no one really implements this by themselves anymore, because we can use PyTorch's AutoGrad, which has some computational facilities to do this automatically. All right, so let's train this then. All right, so we can see after the first epoch, we already got a pretty good training accuracy. It actually goes down, which is interesting. But more interestingly, the cost or the loss here goes also down. So I think this is really due to noise that the training accuracy goes down. It's probably overfitting here. But we see the loss goes down. That's our result. And let's take a look at how it looks like. So we can see the loss goes down. Maybe training it more would be even better. And then let's compute the test accuracy. It's 80%. Let's take a look at how it looks like. So here I'm using function plot decision regions. We have seen that briefly in statistics 451, if you recall that, but you don't have to know this or remember this, because in practice we will actually never really work with 2-dimensional data sets. So we never really have the luxury of plotting it. I'm just using a very simple data set, which is why it's possible here. So here's how the decision regions would look like. So you can see the softmax regression classifier is able to deal with the 3 classes by classifying them relatively well. It's not great in this region here, so could have maybe been improved if the line would be more like this, but it's hard to tell. It's actually not a trivial problem for a linear classifier. A non-linear classifier may have an easier time here in this region. Now, but this is also not the point. Now let's take a look at how we would implement it using PyTorch's module API. So the module API makes many things easier, like I said before. So we can use this linear layer, which is our net input computation here. So actually we don't need all of this part in a real application. I'm just doing this part so that we can compare this implementation to our from scratch implementation, because above I also used zeros. So if I go up, I initialize the weights to zeros. So otherwise, if I don't do that here at the bottom, it will have small random numbers. The small random numbers are good for multi-layer networks, but it would make it hard to, of course, compare then this implementation with our above if we have different starting weights. So we just add this, but in a real case, you would just run it like this. All right. But we will also talk more about weight initialization in a later lecture. I think, like, I would say maybe in 2 weeks I will have a lecture on how we can initialize weights and what these random weights are. And there are some computational tricks to choosing good weights. All right. The forward method is now very simple. We can use the net input computation here via the linear layer, which we defined here. And then here, this softmax is our softmax activation function. We use that from PyTorch now. So f is from PyTorch. I think I imported it at the very top. Let me see. Yeah, so here this is the Torch functional API. So NN stands for neural network, and this is the functional API. Instead of typing it all the time, instead of writing, let's say this dot softmax and do the same for other functions, people usually implement the function API as f just to make it shorter, so you only have to type f softmax basically. So that's just a convention when you work with PyTorch code. Okay. So yeah, and that is basically it. We are using the stochastic gradient descent optimizer here, optimizing the parameters of that model. And this is all there is to it really when we use PyTorch. And training it now, you can see test accuracy is also 80%. And actually, yeah, if you would scroll up, you look at this decision region plot, and this one, it looks almost identical. There is some slight numerical difference. If you look at these values, you 0.558 and minus 0.12. Let me just copy them maybe. There's some slight, maybe not really even. This one is a little bit different, you can see, but it's only like 3 digits after the decimal point. This is just some numerical rounding error, I would say, because we implemented lots of things from scratch, like softmax and the cross entropy function and things like that. And we have the vanilla implementations. There are also some numerically more stable implementations of softmax by adding or multiplying the denominator and numerator by c, so adding log constant to the exponent. That would make it more stable, but then it would change the numbers slightly. I think these differences are because of that. Of course, in practice, you don't want to implement softmax and cross entropy yourself because it's numerically not as stable as, not as fast as the implementations that are already provided. But yeah, overall, we get exactly the same results. I mean, with small rounding differences. Now, this is how we do softmax regression in PyTorch. Let's now take a look at the same thing for the MNIST dataset, because I already showed you the MNIST dataset in the lecture, and so just for completeness, we will actually be working with this more when we talk about multi-layer perceptrons in the next lecture. So what's new now is I'm using a data loader, and this is usually how we load images in PyTorch on other types of data. So here are just some settings for my model, and here the MNIST dataset is already provided in a library. Let me scroll up again. In a library called Torch Vision. It comes with a number of datasets. So if you install PyTorch, it will also, if you use the installer via the website, it will automatically install Torch Vision, so you don't have to install it separately. It usually is included in the command that you executed when you installed PyTorch. So we use this MNIST dataset from Torch Vision, from the datasets submodule. This is just specifying where to store the data. So it will create, if I go here, it will create a data folder next to my notebook here, because I called it data, but you can actually change this to whatever. You can change it to desktop data or something like that. It really doesn't matter. It's just where it keeps the data, so temporarily. So if you go here inside, you will see it will keep a copy of that data. All right. Then it has a test and a training set. So train true, test. This is for testing. If you say train false, I will actually show you. It's a little bit unfortunate that MNIST doesn't have a validation split, but I will show you in the multi-layer perceptron lectures how we also can create a validation split for that one. This one is kind of required. because MNIST is are images, and they come in a, I think it's a PIL, Python imaging library format, and you want to convert them to PyTorch tensors. So this one is converting the image representation in Python to a PyTorch tensor representation. But we will also see later we can use other data augmentation here, like randomly flipping or cropping images. So we will talk about this also more when we talk about convolutional networks. Also, I should say that toTensor normalizes the pixels to 0, 1 range. So it's dividing them by 255. So I should mention that. So we don't have to do our data normalization ourselves. Of course, we could actually do something better. We could standardize them for color images. Sometimes people standardize using the mean and the standard deviations from ImageNet. We could technically also do that for color images. For here, something like MNIST, it doesn't matter at all, to be honest. There's probably no difference in the performance of the model, because it's a very simple optimization task here with stochastic gradient descent. All right, so this is defining the training data set. This is defining the test data set. The difference is really that we set train false and here to true. We only need to download it once, right? So I don't have a download here. Then using the dataset, we define data loaders. So here I'm defining a data loader for the training set. I can set my batch size. I set it here above. That's my mini batch size. I set it to 256. And then whether we want to shuffle or not. So this is shuffling before each epoch. It's shuffling the dataset. Notice that here I'm not shuffling the test set because it doesn't really matter. I'm loading the test set in batches. It's also not really necessary because we don't do any training and stochastic gradient descent on the test set. But let's say if we work with real image data sets like ImageNet, the test set can be quite large and it might not fit into memory. So we can also load it one by one, basically. That's what I'm doing here. Here, just for completeness, this is more like for verifying that everything looks good. So here I'm just having a for loop over the images and labels in the training loader just to make sure everything looks okay. And you can see it's loading the images in this NCHW format. The batch size, the number of color channels. We only have one color channel because MNIST is black and white. And then we have the height and the width here. And the labels, of course, are a vector because, yeah, that's just the numbers. And I should also tell you, okay, these labels are not one-hot encoded. So you can see that they are just the numbers, the class labels, the 10 class labels. It's not necessary to one-hot encode them because PyTorch does it automatically when we call the cross-entropy loss. All right, so here is now my implementation. This is the same as in this from scratch here, so there's nothing really different. Same thing. Yeah, so also notice, so yeah, the accuracy, I'm computing it using a for loop over the data loader. I don't have to go through this. I think this is something you could copy and paste if you need it. Yeah, so the interesting part, what I wanted to show you is, because I don't want to make this video too long. I mean, I could discuss everything, but if you have questions, maybe ask on Piazza, we can discuss this more. I don't want to spend too much time on things that are not that important right now. Yeah, so the important parts are here that we are concatenating. So that goes back to what I've showed you here. So this would be how our image looks like. It's a 3D tensor. One image is a 3D tensor, 28 by 28, and then the color dimension. So if you don't think of the color dimension, it would be a matrix, a 28 by 28 matrix, but we need a feature vector as input. So we would concatenate it to a very long vector, a 28 times 28, so a 784 dimensional vector. So that's what I'm doing here. So I'm concatenating it to a vector. I can maybe show you how that would look like for one given, let's say we take one image. So this would be the one color channel, then 28 by 28. Actually, you can also, I mean, okay, it's fine, I think. So view -1 and 28 times 28. So you can see now it's a one long vector basically. So in this case, I think it's a matrix because we have the first dimension, but yeah. So, but the same thing applies. So here, yeah, we do that for the, so actually this would be for the wedge dimension. One more time, sorry. Images dot, so this should be a 256 times 784 dimensional matrix. So this is for the, this is all basically, this is like how our design matrix looks like. It's then an n times m dimensional matrix now, where m is the features, n is the batches. It got rid of, notice that it got rid of the color channel here. There's no color channel because we only define two axes. If we do it like this, it would have a color channel, but yeah, we don't want a color channel here. All right. Yeah, and then we call our model. Notice when we use PyTorch, we don't use dot forward because it's actually better to just call it like this. It will internally call forward, but it will do some extra checks before it calls forward, as I explained in an earlier lecture. And now the interesting part is, yeah, we compute the cross entropy cost or loss here. And notice that it's important that it uses the logits as input. So it's not using the probabilities, it's using the logits. This was what I explained in a previous video. This is like the slightly confusing part. I explained it in this other previous video. So we have to pay attention that we provide the logits and not the probabilities here. Yeah, and then we zero the gradients, do the backward. We are just averaging the costs here. Don't know why I did that. Don't need that. Oh, okay, I see. I compute the average cost over the epoch. I see. Yeah, so then I'm plotting it. Okay, I need to execute this part. So this cost is the average cost per epoch. I could technically compute the cost by calling forward or doing this one for the whole data set, but it would be more work, right? So you would have to load the whole data set, so I'm just computing the average. Okay, might take a while. It's not too bad though, it's like 0.04 minutes per epoch. It's not even, I don't know if these numbers make sense. 1 minute, yeah, makes maybe sense, yeah. All right, so now, yeah, this is how the loss looks like. You can see it goes down as expected. Let's take a quick look at the test accuracy. 92.16. It's actually pretty good, right? I mean, given that this is an image data set and we only have a linear classifier, we don't even use a neural network, I mean a multi-layer neural network, we already get a pretty good performance. And personally, I also recommend you when you work on classification tasks, always to run also logistic regression classifier or softmax regression classifier as a baseline, just to get a feeling of how difficult the classification problem is, right? So if you train, let's say, convolutional network and you got only 94% with a convolutional network, you would say, okay, this is such a complicated convolutional network model. Why does it only get 94% when I get already 92% with logistic regression? Maybe my model with 94% isn't that good after all. So it's always a good thing to run also logistic regression as a baseline. Yeah, here's just an example. Loading 3 random images from the dataset, 7, 2, 1, and 0. And then here I'm doing my predictions. So I'm calling this one on the feature vectors and then the argmax to get the class labels, right? Because this one would give us just the probabilities. As you can see, so we are taking the argmax. So for the first one, let's take a look. Should be, this one should be the highest. 0, 1, 2, 3, 4, 5, 6, 7. This is the highest. It's actually, should be the highest one. So in this way, we compute the class labels here just to show that these are indeed correct. All right, so with that, this is all I think I have for this from Scratch implementation. And then in the next lecture, I will talk about multi-layer perceptrons.